Now, I'm not going to talk about the way I reversed engineered the vulnerability point and how I found it, because I didn't do any of it. It was another member from the group that released a paper about the patch 2 days before I actually started to work on this patch. So I used his work, and that's again the member I talked about earlier, Michael Haley. So this time there is this load cursor icon from file map. So it loads and passes the file from the memory. File map is the file in the memory, and this is for performance issues probably, to load the whole file onto the memory, and then you can read it faster. So there is a chunk named AnyAge. It's the Any header, and it tells its loader or player how many icons there are inside the animated cursor. And this one is passed later by load AnyIcon. So after we pass the Any header, there is another parser for the chunks of the icons themselves. And this one is done by load AnyIcon. So what we can see here is the malformed animated cursor file, and this is actually the ASCII dump of it, and it was enough for the thing I want to show you. So we can see the ref and the icon, and then the first Any header, okay? Which is correct and in place, and comes here to talk about the next icons it's described. So the first header chunk, and so far so good, everything is fine. The patch was already fixed in 2005, and now you can see. Okay, so this is the trick. The Any header chunk is here again, and this time it's passed by the load Any function that it was supposed to only pass the rest of the icons, and for some reason it passes again the Any header. And maybe it's a problem in the design of the format of animated cursors. I'm not sure, but anyways, it did the job well. So the attack vectors. Actually, Internet Explorer can load the file really easily with style cursor, URL, malformed Any, and you don't have to do anything else. And of course, Outlook and Outlook is vulnerable too because it can run HTML, because it passes HTML, and Windows Explorer, the shell itself, because if you have an .ico file in the folder, shell will show you the thumbnail of this icon and pass the file, and the code will get executed. So about the patcher. So this time we have to patch user32 DLL, and this DLL can be found in all processes, of course, at least the GUI ones. And therefore it requires a memory patching. So instead of going against the Windows file protection, all I had to do is use the non-DLLs. This key in the registry tells the loader to load our DLL file that will patch the file every time again, and in every process. So basically, if Internet Explorer is ran after we change the non-DLL's key in the registry, our DLL will run and do its stuff. So the stuff is magic work that we will soon see what's going on. So this is the load AnyIcon, and this is where you can see the switch, or in assembly, the switch case in C. And this is how it's translated to assembly, and you can see the compare EAX with sequence, list, rate, and the Any header again. So we said earlier that it was passed in the color of the load AnyIcon, and now it's passed again, and later on what really does the overflow is the call read chunk. So we know that we have to patch this function. And this is the xdump of the same code, but I wanted to show you the dwords and the signatures I'm going to look for. So there is the list and the Any header. So basically I want to find the switch the cases of the switch. And if you wonder why this time it's list, and you can read it, and here it's TSIL, it's because the endianity and how it's laid in memory. Okay, so this patch is actually a new technique, and it's about generic patching, and unlikely the earlier patch of VML with the mask, this is a much more, it's a better patch. Let's see why. So we have the read chunk, which actually mem copies the buffer, and it needs a fix. The problem is that there are 3 cross-references, 3 callers to this function, and we only want to patch the one that actually triggers the exploitation. Because, again, we don't want to change match the file as less as possible, touching it, and to not break its functionality. So what we do is searching for a static signature, and this is what I say, like a look back to find a signature, and then disassemble forward until the next call is found. I will show it again. So what we want to find is this dword, the any header, the list, and then we know this is the area in the user 32 DLL that we want to find. And if we keep on disassembling, after the any header, we will reach to this call that we want to patch. So that's why we need a disassembler here. Okay, so now we found the indirectly call to memcopy, because the read chunk itself calls another function that does the memcopy. And it complicates the stuff a bit, and we'll see why. So the fix. So I took the read chunk function and rewrote it with the added validation. And this time I didn't have to crunch the code. I have all the room I needed, and again, it's pre-compiled. So I just needed an assembler and took the code and added the test and recompiled. And there is only one problem now that I talked earlier. The memcopy is the read file PTR copy. So our read chunk, because the nature of the 32-bit and or even in x86, that calls are relative to the current position they are executed. So we have to relocate the address of the call from the read chunk, or the new read chunk, because it's now patched, to read file PTR copy. And therefore, it means we have to find the read file PTR copy, the address of it, and relocate our new function. So what we do is a fix for the pre-compiled call, and again, calculate the relative 32-bit offset of the file. So what we have to do, if we talk about technically about the API to use, you can't use, for example, malloc, because, or memory alloc, however you will want to call it, is because it's in the heap, and the heap is not supposed to be executed, and therefore what we have to do is to use, for example, virtual alloc and supply the flags for telling it is an executable code. So after we did all these things, and this is part of it is in precompiled and part of it in runtime, we have to relocate the original vulnerable call. So the read chunk has to be patched to the new allocated function. So some problems we might encounter. If there are multiple threads, might run the patched code. So if you patch a sequence of bytes while a code is running in, the same code is running from a few threads, you might screw up some of the threads because the code is not synchronized, and it might run some garbage code. So that's why we patch only a dword, and that's the offset we relocate to the allocated place. And there is no problem with it because we can do it atomically. And another thing, that when we search for the signature, the any header and the list, we have to search for a D word, but it must be in a byte aligned, because if you make a C for loop to look for if you scan the list as a long pointer, it will find it in jumps of a D word, and then you might miss the D word you really want to find, because it can be misaligned. So we look for a D word in byte aligned. This is tricky and crucial. And again, to find the call to the read chunk, we have to use the disassembler. Because, for example, if we want to find the E8, that's the byte that means it's a call instruction, and it can appear as a part of another instruction. And then if we run on the code and find the E8, it might be something else, and we can screw up the code and the patch won't work. Therefore, we use a disassembler that will disassemble the stream, and we then get the accurate instruction and its address. And there is another problem with if-then statements, because the way they are generated, it might branch to, for example, there was the comparison with the any header. So if there is a branch, okay, compare EAX with the any header D word, and then there is a JZ. It means take the jump if the value is found, and then you have to follow that branch, because if it generates Z, you have to run with the flow. So you have to be code flow aware and notice this little stuff, because it's important. Otherwise, you can miss the real call you want to follow. So that was it about the honey patch, and maybe, I'm not sure I really explained it well. You will have soon time to ask questions. So I wanted to talk about the sad truth about these patches. So again, about the animated cursor, after the buffer was mem-copied to the stack and it made the overflow, the code only then assured the file. It's verified the size of the buffer only after it overflowed the function. So this is a bit ironic thing. So another thing is the VML. The VML vulnerability didn't exist back in Internet Explorer 7, but only some versions of it, and of course now it's all already patched. But I ask myself, if it's not patched back then when the 0 day is, if it's already patched back then when the 0 day was released or in the wild, then why Microsoft didn't patch the Internet Explorer 6 in time or before the 0 day? So they knew there is a bug and they didn't patch Internet Explorer 6. This is pretty annoying, but maybe because they have lots of source code and other teams that work on Internet Explorer 6 and 7 and they don't cooperate well. I can't answer really for that. Another thing is that, and notice this, Internet Explorer 5 had the validation test for the VML. So if you had basically Internet Explorer 5 today that you won't do it for any sane reason, then you would be protected. So eventually, Xert is just another third party and that supplies patches. So I'm going to say it simple as that. Do not use third-party patches. Yes, Gil Dabach said it now after all his hard work and for a reason, but let's see why. So do you really trust the people that don't have the code or didn't write the code themselves? I mean, you have the source code, or actually only Microsoft has the source code, but notice the emphasized word source. It means we have the code, we can disassemble or reverse engineer the code, but the source code is maybe what matters, but maybe not, because after all we did a